In this video, we're going to be looking at Newton's laws with applications. We're going to be dealing with the normal force and weight and seeing how your weight would also change when you're in a non-static environment. To start, we're going to look at the box that's sitting over here that's just on the table. Here, let's give the box a weight of 40 newtons. So we're saying that the box weighs 40 newtons. So its weight would be a downward vector due to gravity. Now, since it's sitting still on the on the table, that means that the table is also pushing up with a force equal to its weight of 40 newtons. So the normal force is pushing back up at an equal force to that of the weight. So when it's sitting still, the normal force is equal to the weight. Now let's say I'm pushing down on the box as well. So the box is still sitting there, but now I'm pushing down with another 20 newtons of force. As long as I don't break the table, that means that the table is able to provide an additional 20 newtons back up. So once again, the total force down has to equal the total force up. So here, the weight plus 20 newtons is now equal to the normal force. So 40 plus 20 is still equal to 60. Instead of pushing down, if I were to pull up on the box, I would be alleviating some of the weight. So if I were to pull up with a force of 15 newtons, now the normal force would change as I'm no longer adding 20, but now I'm subtracting 15 newtons. So in this case, the normal force would only be 25 newtons. Well, let's look at what would happen if I was in an elevator moving up and down. Here we're just going to pretend this person is a little dot here. Gravity is always going down. Alright, so if he's just sitting still, even if I'm moving at a constant velocity, if I have no acceleration, whatever my weight is would be the same reading at the scale. So we're just going to say this guy weighs 100 newtons to start with. So if he weighs 100 newtons and he's traveling at a constant speed, the scale reading would be 100 newtons. Now we're going to look at this situation over here. If he is accelerating upward, he has an upward acceleration. Down here, if he's the little ball in the middle, there's an upward acceleration, an upward force, and a downward force due to the force of gravity. These vectors are heading in opposite directions. So inherently, you would want to subtract them. But in actuality, it's like a tug of war. What's happening is gravity is pulling down, and the tension on the rope for the elevator is pulling upward, and they're pulling you in opposite directions. So the total force here is the addition of the two. So whatever your upward acceleration is, plus your force downward, is going to be the total scale reading. So let's say you're accelerating up at 2.0 meters per second squared, and gravity's pulling down at 10 meters per second squared. So force is equal to mass times acceleration. We said since he weighs 100 newtons that he has a mass of 10 kilograms. And here I would take my 10 meters per second squared and add 2 meters per second squared. So 10 times 12 equals 120 newtons. So in this case, the scale will read 120 newtons. Now, over here, if we're looking at this, now the elevator is accelerating downward. When the elevator first moves downward, you start to feel a slight bit of weightlessness. Here is the same scenario. Now both of my force vectors are pointing down. But in this case, I don't add them together. Here I subtract them. So if I'm accelerating downward at 2 meters per second squared, once again, F equals ma. So 10 kilograms, 10 meters per second squared minus 2 meters per second squared. So 10 kilograms times 8 meters per second squared equals 80 newtons. So here the scale would only read 80 newtons. So when I'm going down an elevator, my weight will always be less. When I'm accelerating up an elevator, my weight will always be more. And that ends this session.